Here's an introduction to how we can use calculus to compute the arc length of any arbitrary curve. We already know how to compute the arc length of a curve that looks like this, for example. This is called a circle. If we wanted to take a piece of that circle, like say the piece subtended by an angle theta, the arc length of that can be computed by s equals r times theta, where r is the radius of the circle. But this is not the pre-calculus basis that we use for setting up the integrals, because there's an even simpler curve for which we know how to calculate the arc length. Do you remember what it is? That's right, it's a line. If I'm going to take a piece of the line defined by delta x and delta y, the arc length of that piece of the line can be computed using the Pythagorean theorem. S equals the square root of delta x squared plus delta y squared. And this is actually going to be our pre-calculus basis for computing the arc length of the arbitrary curve. So we'll take an arbitrary curve, and of course, since it's calculus, we're going to divide it up into lots of little pieces. And then we pretend that each little piece is actually a line segment. Next, we zoom into one particular line segment on that curve. And then we name the tiny little delta x and the tiny little delta y. And since we're taking a limit so that this is an infinitesimal, we'll call them dx instead of delta x, dy instead of delta y. Then we'll calculate ds, the little piece of arc length of just that line segment, using our pre-calculus basis, equals the square root of dx squared plus dy squared. But it's unclear how you would use this formula to set up an integral, because we're used to finding expressions that have a real number times dx. So I'm going to do a little tricky algebraic manipulation on this. First I'll rewrite it with a little extra space. Now I'm going to stick a dx on the end. And I'll compensate at the beginning in front of it by writing a 1 over dx. And that looks kind of weird, but look what happens when you put it inside of the radical as a 1 over dx squared on the inside. Then you can distribute it over the two terms, and it becomes dx squared over dx squared plus dy squared over dx squared inside the radical. And the whole expression can be written as ds equals the square root of 1 plus y prime squared dx. And this is now what we're going to use to set up the integral. But don't just assume this formula is correct and start working with it. First of all, think about it in a simple case and see if it makes sense to you. And then if it makes sense, then try it out on a curve for which you don't need it. Take a circle and see if you can use this integration formula to come up with the formula for the arc length of a circle. All right, we're looking for s equals r theta, where theta in this case is now defined in terms of the angles alpha 2 and alpha 1. So theta is the difference alpha 2 minus alpha 1. And the circle is described by a function curve y equals the square root of r squared minus x squared. There's one more thing we need to set up the integral, and that's the starting and ending values of x. So I'll call them x2 and x1. They're sort of named in reverse order because turns out alpha 2 is the bigger angle and corresponds to the smaller value of x. So here's our integral. S is the sum of ds's. It's the integral from x2 to x1 of the square root of 1 plus y prime squared dx. That's all I'm going to give you. See if you can take that, differentiate to find y prime, and set up the integral and do the algebraic manipulation and see if you can get all the way to s equals r theta. I will give you one hint. You might have to pay attention to this angle up here, which is the complement of alpha 2, and this angle over here, which is the complement of alpha 1. Those angles will become important when you think about the result of the integration and the triangle definitions of the trig functions.